We're going to talk about how to calculate the mass percent of a particular element in a compound from using the formula. So the example we're going to do is the amount of iron in iron 3 oxide, Fe2O3, which is basically rust. So we want to know in a compound of rust how much iron is there by mass. Okay, so the general formula is going to be we need the mass of the element we're interested in, the mass of Fe per formula unit, and divide that by the molar mass of the compound. And once we have that ratio, we take that and we multiply that by 100% to get the mass percent. Okay, in order to do this, we need to know the molar mass of the compound. Now, the molar mass of the compound, Fe2O3, is going to be the sum of the molar masses of the individual atoms. So for Fe2O3, where we have 2 irons, each of those has a molar mass of 55.847 grams per mole. And then we have 3 oxygens, which each have a molar mass of 15.999. So we add all those up, and we get 159.691, and again the units are grams per mole. Alright, so now we're set up to do the calculation. The mass of iron per formula unit, well, there's 2 irons in each formula unit, so we need twice the molar mass of iron, 55.847. That'll be the top. The bottom is the entire molar mass of the compound, 159.691 grams per mole, and the top is also grams per mole. Then we divide, multiply by 100%, and we get 69.94% iron in iron 3 oxide. Now you try a similar calculation, this time for the compound NaClO2. So that has 3 different elements in it. Try calculating the mass percent of sodium, of chlorine, and of oxygen in that. Stop the video until you have done that calculation. Alright, so there's 3 different elements. For sodium, we're going to use the mass of sodium per formula unit, and there's 1 sodium in there, so just the molar mass of sodium, 22.990 grams per mole. Divide that by the total molar mass for the entire compound. Okay, so we need to calculate that. It's 1 sodium, 22.990, 1 chlorine, 35.45, and 2 oxygens. So that's 2 times 16.00. I'm rounding a little bit here more than the other one. And so I'm getting a molar mass of 90.44 grams per mole. Depending on how much accuracy you need in your calculation, you may choose more or fewer sig figs than I did. Alright, so again, back to the sodium, then the denominator is going to be the molar mass of the compound, 90.44 grams per mole, times 100% gives you 25.42% sodium. We can do the same calculation for the chlorine. There's 1 chlorine, so the numerator is 35.45 divided by 90.44. Again, everything's grams per mole. Times 100%. So the chlorine turns out to be 39.20%. Finally, the oxygen. There are 2 oxygens, so the numerator has to be 2 times the molar mass of oxygen divided by 90.44. Keep my units there, grams per mole, times 100%, and that was 35.38%. Now, since I did all three parts of this compound, they should add up to be 100%, since I calculated for all of them. And if you add these up, these three will sum to 100% exactly. Okay, now we're going to switch gears and go backwards. Instead of trying to determine mass percent from a given formula, we're going to try to determine a formula if we're given mass percent. Now, this formula will not necessarily be the molecular formula, because we will simply get a ratio of the different amounts of each atom. So what we will get is actually the empirical formula. So let's do an example. Let's say we know we have a compound that contains only chlorine and silicon, and we know that this chlorine is 79.1% by mass. We want to know what is the compound, at least the empirical formula. All right, so the process is that we choose a sample size, and usually the easiest size to choose is 100 grams. Okay, so we're going to say, let's say we have 100 grams of this sample. We know 79.1% of it is chlorine, so then we know we have 79.1 grams of chlorine in this compound. Since silicon is the only other compound in it, then by subtraction we know we have 20.9 grams of silicon. All right, but ratios in formulas are in moles, so we need to convert both to moles. So first we'll do the chlorine, 79.1 grams of chlorine, and the way to convert it to moles is to use its molar mass. The molar mass of chlorine, 35.45 grams per mole. That gives us 2.23 moles of chlorine in each 100 grams of compound. Same thing for the silicon, 20.9 grams of silicon. Molar mass of silicon is 28.09 per mole, grams per mole. And that gives us 0.744 moles of silicon in our little sample of 100 grams. Now we're going to take mole ratios, because the formula is basically a mole ratio. At least the empirical one is. So we're going to take the larger amount and put it over the smaller. You don't have to do that, but we'll take the larger one and put it over the smaller. The larger one is the chlorine, around 2 moles. Silicon is less. So we'll take the moles of chlorine and divide it by the moles of silicon, which is 2.23 per 0.744 for the silicon. And that gives us approximately 3. Now we are looking for an integer ratio, so the fact that it's close to 3 tells us the ratio is 3, and then our empirical formula since we know the ratio of the moles of chlorine to silicon is 3, we would say the formula is 1 silicon for every 3 chlorines. So that is the empirical formula. From that we can guess a few possible molecular formulas. Now the molecular formula could just be SiCl3, but it's going to be some ratio of 3 to 1 in the silicon. So it could be that, or it could be twice that. Okay, it's 2 silicons and 6 chlorines, or it could be 3 times that, etc., etc., etc. Those are all possible molecular formulas that would have this particular empirical formula, SiCl3. Okay, it's time for you to try doing the same thing this has two compounds, both of which have only hydrogen and oxygen, okay, H and O. And compound A has 11% by mass of H, compound B has 6%. So you're going to get two different empirical formulas, one for A, one for B. All right, let's get started. We know what the mass percent of oxygen is by subtraction from 100. Okay, if H is 11%, then we know oxygen must be 89%. And if H is 6% in compound B, then we know oxygen is 94%. All right, and if we do the first step, which is assume a mass of 100 grams, then we also know that we have 11 grams of hydrogen in this compound and 89 grams of oxygen in compound A. Compound B, we have 6 grams of hydrogen and 94 grams of oxygen. All right, to convert each of those into moles, because the empirical formula is a mole ratio. So we'll start with hydrogen, 11 grams of H. Molar mass of H is about 1.008. That gives you 10.91 moles of H. I'll do oxygen, 89 grams of oxygen, molar mass of oxygen, 16, which gives me 5.56 moles of oxygen in compound A. Let's do the same for compound B. 6 grams of H. Same molar mass as we just did. And this time we get 5.95 moles of H. I'll make that look clearer. And for oxygen, 94. Gives me 5.88 moles of O for compound B. Now take those and we do ratios of the larger over the smaller. For compound A, that's 10.91 moles of H over 5.56 moles of O. That ratio is approximately 2. For compound B, the ratio is 5.95 moles of H over 5.88 moles of O. Those numbers are almost the same. That ratio is about 1. Okay, so the empirical formula for compound A, it's 2 to 1 hydrogen to oxygen. That sounds like H2O. For compound B, it's a 1 to 1 ratio, so we can call it HO. Those are the empirical formulas. We can also talk about possible molecular formulas. Now H2O is a compound we know, but if that were not it, it could be H4O2, etc., etc. HO could be any ratio with 1 to 1. So H2O2, H3O3, etc., etc. are all possible molecular formulas.